Okay, Brent, so what are all these black snaky looking things down here?
Okay, so the station boards have to fan out or send the data to every correlator board. And so coming from every station rack is a big star configuration of cables going to every baseline rack. And there's about 30 miles, depending on how you measure it, of cables in the floor. None of that thick cable. That thick cable is a bundle of 64 single pair cables. So there's about 30 miles of the single pair cable.
Is this your average cable that you might find attached to your television or something?
Actually, for HD TV systems, you have bandwidth in the HD TV cable that's comparable to that bandwidth.
So Brent, give us a brief description of these cables. What makes them so special?
Each cable consists of 16 pairs, differential pairs, and each differential pair carries a gigabit per second. And the cabling that we chose and the connectors allowed us to cross-connect the signals from the station boards, the antenna-based processing boards, through a distributed crossbar switch to go to the correlator board, so there was lots of flexibility in the system. So you could be doing a small bandwidth with using all of the correlator, or a large bandwidth doing lots of the correlator. So it bought us lots of flexibility.
So now that we're standing here, there's one heck of a gale of cold air pouring out of the floor.
Yeah, I'm freezing.
So you want to talk a little bit about the cooling requirements of this machine?
Yeah, so the correlator itself, the power plant is rated for about 170 kilowatts. It's a 48 volt DC power plant, such as you might find in your telephone central office. And each of the boards, the station boards, take about 600 watts apiece, and the baseline boards take about 500 watts apiece. So adding it all up with the fans and everything is about 156 kilowatts. And well, that's the heat that is generated by the correlator. Yeah. So then, of course, you need the HVAC, the cooling systems to keep it all cool.
Right.
And a big part of it is the HVAC systems pressurize the floor with cold air at about 10 or 12 degrees Celsius. And then that air goes up through the racks and cools all the boards.
So by holding this door open, we're probably warming things up a little bit. So
not really, actually. There's a lot of pressure in the system, and the fans draw a lot of the air through the board, so it really doesn't affect it that much.
Oh, okay.
But it just makes us really cold.
Okay, let's go to the front side of a station board.
So these fibers carry the signal from each of the antennas. They're labeled by antenna numbers and such. Each antenna goes to one of these so-called station boards. And what that does is it splits up this 128 gigabits into small enough chunks that we can do the cross multiplies on the baseline board that we saw before. So that's what all this stuff coming in is. And then these are actual communications, command and communication signals coming in here. So this is the clever part of this design is you take this very wide bandwidth coming in from each antenna, you split it up into small enough chunks to process it. You do that processing independently on each of those baseline boards, and you get your signals out. Since all this is done digitally, you can then stitch the narrowband multiplies that you did back together to form one really big wideband product at the end, which is what the astronomers want. And because, as Brent said, he's got all these cables hooked up in the back so that you can send signals from here to one place or to another place or to all sorts of very different places. It's very flexible, so you could use many different baseline boards to do the multiplies for one small set of frequency space and get millions of frequency channels. Or you could do the entire 2 gigahertz wide spectrum, or 16 gigahertz actually total, and get only something like 30,000 channels.
Right.
So that flexibility is very useful for the astronomer. You can get maximum sensitivity to wideband systems, or you can get the perfect spectral resolution to zoom in on a spectral line over here, and another one over here, and another one over there. And you can get it all at once.
So speaking of maxima and minima, what is the finest frequency resolution that this correlator is capable of?
So the finest frequency resolution is a bit under 1 hertz, and that was set by the desire to measure the finest possible, the narrowest possible line from an astronomical source. Because when a signal travels through interstellar space, it's broadened slightly by by the material in interstellar space. And if you take any signal from outside the solar system and propagate it through the solar wind, basically it becomes of order 1 hertz wide. And we wanted to build this correlator for the ages, basically, so it could do any problem we could possibly think of doing. Right. And the amazing thing is that Brent and the folks in Canada managed to do that.
Right, and I think the narrowest bandwidth application that we have is on the bistatic radar reflections. Right?
Right, so the narrowest one that we've thought of, I'm sure people will be smart enough to come up with others, is looking at radar signals that you bounce off of asteroids. And when you bounce radar signals off a rotating body, you get slightly different frequencies back depending on how fast it's rotating. Right. And with this kind of spectral resolution, we can actually make images and watch different parts of the body rotate at very small speeds, less, centimeters a second.